Hello class, welcome to today's lesson, which is lesson 3, and it's about getting the trigonometric functions of any angle. This is a new word, any angle, any angle. Okay, so why? Why do we need to do this? Because if you notice, we have a necessity for an extension of the definition of trigonometric functions. What do I mean by this? So far, and I'm gonna do this in yellow over here, we have only defined the trigonometric functions. These functions only have meaning so far in regards to right triangles, okay, and more specifically in regards to its two acute angles. This one, which I may call angle A, and angle B. Angle C is a right angle. We have only defined the trigonometric functions for angle A and angle B, if you remember. I never defined what, for example, this could mean, the sine of angle C, which is the sine of 90. We don't know what that means yet. All we have defined is that if this is my triangle and these are its sides, the catheti, try to remember that word, cathetes, and the plural is catheti, and this is my hypotenuse. Then I have only defined that the sine of A is equal to its opposite cathetes over its hypotenuse, which is C. The cosine of A is equal to the adjacent cathetes over the hypotenuse, and that tangent of A is equal to opposite over adjacent cathetes. So this is all we have defined so far. So, for example, something like, let me erase all of this now. For example, this triangle right here, if I give it to you and I tell you solve this triangle, and remember what that means is finding all its features, you won't be able to write something like this. For example, if you wrote something like this in this context, it has no meaning yet. Why not? Because the angle A is 120 degrees, which is an obtuse angle, and there is no definition for this type of angle. For the trigonometric functions of this type of angle, greater or equal than 90 degrees, we yet have no definition for that. And so you cannot, at least you cannot manipulate this triangle by starting to write things like this. This will be completely undefined. And so we have a problem, right? We have a problem. It's very similar to the problem that at some point we faced in our history at some point. For example, many years ago, thousands of years, okay, I'm talking about those periods of time. The only types of numbers that we had at first were, natural numbers: 1, 2, 3, 5, 100, etc. These are what is known. This is what is known as the natural numbers, and these are the numbers that we started with. Okay, these were the first creation, and they sufficed for a long period of time. This was enough. Okay, perfect. Now at some point, the the ideas and the complexity of life gave birth to a necessity. For example, I don't know, try to imagine a piece of bread and people sharing this piece of bread. So maybe you're gonna share this piece of bread between two people. Okay, you're gonna cut it, you're gonna part it, and now you have two pieces of bread. And if people called all of these pieces of bread by one, this is one piece of bread. Okay, this is the numerical representation of this. Then what number could represent each of these parts? You see, it's not going to be one, because it's impossible that something smaller than the whole bread will be greater than 1 because all of these numbers are greater than 1. So we had to invent a new number, which is the fractions, right? So we call this, okay, we're gonna invent another type of number, and we're gonna call these two things 1/2. You see? So we had the need to invent or to extend our system, which only comprised these numbers, into a larger system that now comprised all of these numbers 1, 5, 3, etc., and also these new numbers 1/2, 1/3, 2/3, etc., in order to be able to partition things and give numerical representations to these other smaller things. You see, so that was a natural extension. This is an extension. You go from this to this, and this is a larger extension that also contains your previous definition of what number was. And this happens all the time. And then we had the need to invent the negative numbers. You see, when we had commerce, when we started doing a lot of commerce between different regions and different towns or different countries, then you create the concept of debt. Okay, some people have money in their pockets, some people have debt, which is that you owe somebody some money. And what could be a numerical representation of that? Well, they had to invent another type of number, which we now call the negative number. If I say that you have um, an amount of money of minus 3,000, okay, or that this is your balance, what I mean is that you have a debt of 3,000 pesos or whatever. You see, and now you extend your system into an even larger system. Now you have the natural numbers 1, 2, 3, the fractions, and the negative numbers of all of this, right? And you see, extensions are very natural in mathematics and in science and in technology, and they arise because of a necessity. Always, almost always, they arise due to a necessity. And so that's what we're going to do today. We're going to extend our definitions of trigonometric functions so that now we can talk about the trigonometric function, not just of acute angles, but any angle whatsoever. So that's the philosophical or the mm, meta mathematical context of all of what we're going to do today. Okay, so this is done. So number two, uh, we have to define what this means. An angle in standard position. I'm going to define this concept. An angle in standard position. What is an angle in standard position? Okay, first, you draw your Cartesian plane. And what you're going to do is this. You're going to draw an angle somewhere in here. If you do it in this specific way, in which the initial side of the angle is lays on top of the x-axis, in this way. By the way, this is called the vertex. I forgot. This is the vertex of the angle. Vertex. Okay. If you lay down or if you draw an angle in such a way, such that its vertex is at the origin, right there. Okay. The corner of the angle, so to speak, such that the initial side is on top of the x-axis, like so. Initial side is over here. Then that's an angle in a standard position. That's what it is. Okay, in this case, this angle is called theta. It rotates counterclockwise, and we call the terminals. We call this side of the angle the other side because any angle has two sides. We call it the terminal side. Okay, so that's what an angle in a standard position is. The vertex is at the origin. The initial side is on top of the positive x-axis, and that's it. Okay, we call the other side the terminal side. So that there you go. That's what it means. I'm gonna give you another examples of angles in standard position. Look at this angle. Initial side, the vertex is at the origin. The initial side is on top of the positive x-axis. Okay, And that's it, right? This angle theta is rotating this little much, and this is its terminal side. And the same here, look at this one. We have the initial side of the angle is right this one, and then you rotate the angle in this fashion up until this place, and so this is its terminal side. Now I'm gonna give you examples of angles that are not in standard position so that you can tell the difference. For example, if I draw an angle in this way, maybe I'm gonna draw its initial side in here. This is its initial side, and then I'm gonna draw the angle in this way. Perhaps I'm gonna rotate in this direction up until this point or this place. Therefore, its terminal side will be this terminal side. Let me label the angle. Always try to label your angles, give it names. Theta. Theta is a very popular letter for angles. Okay, so look at this angle. Its vertex is at the origin, perfect, but its initial side lays along the negative y-axis, you see? And then the angle rotates in this direction. This is its terminal side. There is nothing wrong with this angle. This is a perfect angle. You know, it's just as good as this one. But we don't call this angle an angle in standard position. Why not? Because it doesn't satisfy my definition. My definition was, one more time, the vertex at the origin and the initial side of the angle laying on top of the positive x-axis. That's it. You see? That's it. That's what it means. So this is not an angle in standard position. Okay, next, let's talk about positive angles, because we also have this adjective, positive and negative, in regards to angles, and now you can understand what that means. Positive angles, negative angles, and coterminal angles. Okay, let's see what this means. One more time, you're always going to be drawing the Cartesian plane in trigonometry. Well, almost always. Try to do it good, okay? Try to label the axis, try to draw these arrows. What these arrows mean, I don't know if I've told you this. Uh, these arrows are not embellishments, okay? These are not just so that this looks good. This has a meaning in mathematics, the arrow. What this means is the direction in which the increasing numbers go. You go from negative numbers, negative, negative, less negative, 0, positive, positive, more positive, more positive, more positive, etc. So this is the direction in which the positive numbers are encountered, so to speak. If you walk in this direction, you're going to walk towards more positive numbers. And the same for the x-axis. So when you draw something like this, it's like where do the positive numbers go? Do they go in this direction, or in this direction, or in this direction? You see what I mean? If I write something like this, which is also perfectly fine. It's perfectly fine doing this. What I'd be telling is that the positive numbers are encountered in this direction. So 1, 2, 3, -1, -2, etc. And the same for y. This has nothing wrong. There's nothing wrong about this. The fact that most of the time we do it this way is just a convention, guys. It's just a habit, but there is nothing wrong with this as long as you set down your arrows. And that's why when people do it this way, that's completely wrong. Even like professional teachers do this sometimes. This is wrong, because you will be telling that positive numbers go in both directions. Not good. Not good. This is the good way to do it, the correct way to do it, by the opinion of most mathematicians. Okay. Okay, so I was saying positive angles, negative angles, and coterminal angles. Okay, let me draw a an angle theta in standard position. So I'm gonna draw its initial side over here, initial side, and its terminal side over here, terminal side. And I'm gonna say that the angle theta rotated in this direction, counterclockwise, counterclockwise. This is counterclockwise. Okay, so this is theta. Okay, I'm gonna say that theta is positive when it rotates counterclockwise. Okay, like in this direction. In this case, this theta is positive because it's rotating counterclockwise. Now, let me draw another angle. Also in standard position. Here you go. This is the initial side. This is also its terminal side, but pay attention how I'm gonna draw the angle now. I'm gonna draw it in this direction. This is its initial side, so I need to start the angle from this side. I need to start drawing it from here. But if you notice, I can go in two directions possibly. Counterclockwise, I can do this, or I can do this in the other direction, which is clockwise. Now let me do it in this way, clockwise. So now this angle, let me label it with another letter. Let me call it alpha. This angle is alpha, and we say that alpha is negative when it rotates clockwise. Okay, so alpha is negative and theta is positive. And if you notice, I tried to draw them like in the, with the same initial side and the same approximately the same terminal side. And that means that when you have two sides that are the initial and the terminal side of an angle, you can actually have many different angles that have these two sides as their sides. Okay, for example, if it's gonna be clearer if I draw angle alpha in here. Look, if I draw angle alpha in this way, then both theta and alpha have the same sides, the same initial side, and the same terminal side. So two sides, whatever, can determine an infinitely number of angles. Because let me do another one in red. No, in what is this color? I don't know. So what about this angle, guys? Can I do this? I'm gonna create this angle. I'm gonna go this way, and I'm not gonna stop right there. I'm gonna continue. Okay. So how many degrees have I covered already? It's a full turn. So I'm at 360 degrees, right? And I can continue, no problem. Nothing can stop me. And now I'm gonna stop. I'm gonna decide to stop right there. There is nothing wrong with this angle, the one I just drew. Let me call it beta. Okay, this big angle is beta, and beta also has the same initial side and the same terminal side as theta and alpha. Of course, beta is a large angle, is greater than 360 degrees, but there is nothing wrong with it. You can also do this type of thing. Okay, so now you know what positive angles are, the ones that rotate counterclockwise. Memorize this, counterclockwise, positive. And negative angles are those that rotate clockwise. Okay, perfect. So we have this down and also this other definition. And then finally, what are coterminal angles? Well, unknowingly, I already drew three coterminal angles in here. Coterminal. What does that sound like? Coterminal. What that means is that they have the terminal sides equal to one another. Okay, all these angles have the same initial side because every angle in standard position has to have the same initial side. It's always this one. But when you have angles that have the same terminal side, in this case theta, alpha, and beta, all of these end in this terminal side, then we say that these three angles, theta, alpha, and beta, are coterminal angles. Coterminal angles. And what that means is they share the same terminal side. That's what it means. Okay, so we have three definitions. Most of these definitions are actually pretty pretty easy to understand, and you don't have to memorize them like with precise words or anything. You just have to understand the concept and explain them in your own words. Okay, so now we have all the context in order to define all of this stuff that I've talked about. It's just the context in order to define what we wanted to define in the first place, which is the definition. I think this is point number 4. The definition of the trigonometric functions of any angle whatsoever. Okay, so how do we do that? We're gonna do it in this way. Okay, what you do is this. So let's say that you want to define the trigonometric functions for an angle theta. What we do is this. We're gonna draw such angle in standard position. Okay, initial side. And let's suppose that this is the terminal side of theta. And let's suppose that theta rotated in this direction. By the way, this is also very important, guys. This little arrow here, this one, it's extremely important because this tells you the direction of the angle. This tells you the direction of the angle. If you take away this little part, you cannot know in what direction it's the angle is rotating. Okay, you have to place it always. Okay, so this is theta, and we define the trigonometric functions of theta in the following way. What you're gonna do is you're gonna spot. Let me do it here. You're gonna spot a point on the terminal side of theta. Any point, it doesn't matter. You look at the terminal side and you just place a point right there. Okay. Now this point has obviously two coordinates. Its x coordinate and its y coordinate. You see? That's also very, very simple to understand. And this point, let me call it point P. This point P also has another feature, which is its distance from the origin. This is the origin, this is the point, and this is the distance from the origin to the point, or from the point to the origin, it doesn't matter. And most people call this distance r. So I'm gonna place it here. This is r, the distance from the origin to the point. This is r. Okay, and now with this diagram or this configuration, with this point chosen on the terminal side of theta, with its two coordinates x, y, and with its distance from the point to the origin, now we can define what we are going to understand as the sine of theta, the cosine of theta, and the tangent of my angle theta. Okay, this definition is this. the sine of theta will be equal to the y coordinate of P over its distance from the origin, r. The cosine of theta will be the x coordinate of P over r, and the tangent of theta will be y over x. These are the definitions, guys. These are the definitions of the trigonometric functions of any angle. If you want to find the trigonometric functions of any angle, just draw the angle. I'm going to do it one more time. Let's suppose that you want to find the trigonometric functions of 210 degrees. Let's suppose 210 degrees is approximately this angle. This is its initial side, and this would be its terminal side approximately, and this is 210 degrees, more or less. Let me call that angle theta, 210 degrees. And all you need to do to get the sine of 210, the cosine of 210, and the tangent of 210 degrees, you have to do this. One more time, let's do it. You draw the angle in a standard position. Next, you choose any point. It doesn't matter what point, any point over its terminal side, any point. This point, being a point, has two coordinates, coordinate x and coordinate y, and also it must have a distance from the origin, right? Let's call that distance r, all of this. That's it. That's it. With these three values, with these three numbers, x, y, and r, you can find the trigonometric functions of this angle. The sine of 210 degrees will be equal to, according to this definition, the y coordinate of this point over the distance from this point to the origin, and so on for the rest. That's how you do it. That's the definition. It's an operational definition. I'm telling you what to do in order to calculate the sine of any angle. I'm telling you, draw it, draw its terminal side, choose a point in the terminal side, do this, do that, and therefore these are the definitions. Okay, now let's talk a little about this, because I know that I know what you're thinking. Like, why did anybody think about defining these functions in this way? How can this be an extension? Okay, perfect. Let me tell you why. This definition, guys, is an extension. I've been telling you that word quite a lot today, because if you notice, this definition actually contains the previous definition that we have for trigonometric functions. When you apply this definition only for acute angles, and those angles will be located in this first quadrant, right? Because if I draw the initial side of the angle, there you go. And if I stick to only acute angles, the angle will live, so to speak, in this first quadrant, right? The terminal side cannot go either to the second quadrant or the third quadrant or the fourth, because that would make the angle more than 90 degrees. So for acute angles, the terminal side will be somewhere in the first quadrant. So this is it. This is the terminal side, okay? And then, for example, this could be my angle theta, okay? And if I wanted to get the trigonometric functions of this angle theta, I'm gonna go back to my definition, to the way these things are obtained, and I go, okay, I choose one point on this terminal side, any point, it doesn't matter. I label it, let's call it P, and this point P has coordinates x, y, and it has a distance from the origin, which is r, which is all of this thing. Okay, let me Let me draw it better. All of this is R. Okay, perfect. And therefore, that's it. That's it. That's all I need. I need to draw this, and therefore, this, well, it's already here. The sine of theta will be y, the coordinate y of this point over r. The cosine of theta is this, and the tangent of theta is this. Okay, now I'm gonna demonstrate to you that these definitions would actually be the same definitions we already have for the trigonometric functions of the acute angles of a right triangle. Why? Because all you have to do is this. Take this point, draw a perpendicular to the x-axis, like so, you see? And now you can clearly see that we have formed a right triangle with a hypotenuse of r, with a cathetus, this one, whose length is y, and with another cathetus, which is this one, whose length is x. You see? And therefore, don't even look at this. Don't even look at this. Therefore, if I give you this triangle and I tell you, give me the trigonometric functions of theta, you're gonna have to write from what we have seen. You're gonna have to write, okay, the sine of theta is equal to opposite cathetus, which is y, over hypotenuse, which is r. You see, cosine of theta is adjacent cathetus, which is x, over the hypotenuse, which is r, and the tangent of theta is going to be equal to opposite cathetus over adjacent cathetus, so it's going to be y over x. Now look at these things which we already defined before, and look at these other new things, which is the most general definitions of the functions. It's the same thing. It's the exact same thing. You see? So basically, this new definition of the trigonometric functions of any angle, in the way we have arranged the definition, this new definition contains completely the previous definition that we have written for the trigonometric functions of an acute angle of a right triangle. You see, we had um, a previous definition, okay, and now let me represent it visually in this way. We had a previous definition, and now what we just did by doing all this explanation is just extending that definition to a larger definition, okay, that contains my previous definition. That's what we have done. I hope you understand that. I'm gonna take your questions in a moment in case you're not grasping what I just said. And that's it, guys. You see, that's how this new definition of the trigonometric functions work. Okay, I'm gonna stop this video right here. I'm gonna do another one for examples, and let me take your questions. Okay,